4.3, periodic table. How did Mendeleev first arrange his periodic table? He based everything off of atomic masses and the properties, and eventually people realized that mass typically does go up, but more importantly, and you see the repeating patterns if you arrange it according to atomic number, which we now know is the number of protons. So when you arrange the periodic table according to atomic number, the properties start repeating. Anytime you have a repeating property, you know that they should go in the same column or the same group. And that's how they knew to have only the 8 groups. You start with the S1 and the S2, and then you drop down here to the Ds. Let's not count those yet. And then the Ps. So you have 2 here and 6 here, and you add those up and you get 8. And why not 9? Well, because the 9th element, the one that would be right here, actually has the same pattern or the same properties as the element over here. So that's how we know to start a new row, and so forth. It said not only did Mendeleev organize the elements in a useful manner, but he also used them to predict properties of undiscovered elements. And he looked at the properties of elements above and below and to the left and the right and basically averaged them. And he said that the missing element that should be in this block, the properties are going to be in between the elements here and the properties of the elements here. And he figured out these, predicted these properties, and sure enough, when they discovered those elements, they did in fact have properties that were right in between those two. And the same thing with top and bottom. All right, the periodic table. Metals are on the left, nonmetals are on the right. You should know your properties of metals. I did say list 3, but make sure that you're familiar with all of these and what they mean. Make sure you know what ductile means, malleable. And the same thing here, list 3 properties of nonmetals. Again, I listed some more, but you should be familiar with all of them. So pause that, make sure that you've got them all on the list and or in your head. All right, periodic table group names you should be familiar with. This is just a matter of memorization. But the alkali metals and the alkali earth, this one has 1 funny name before the word metal. This has 2 funny names. So just remember, alkali is group 1, alkaline earth, 2 names, group 2. Halogens are group 7, and 8 is noble gas. By now you should know what they end in and how many valence electrons. And don't get tripped up with helium. Helium only has 2 valence electrons. Elements in the same group have similar properties. Why? Because their electron configurations are all the same. They all end in the same thing. And as a result, they want to do the same thing to get that stable, happy configuration. So they all, like in group 1, they all have 1 valence electron, so they all want to lose 1. In group 7, they all have 7, so they all want to gain 1, and so forth. Elements in the D block are referred to as transition metals. S and the P block are representative elements. These guys represent the rules. They are predictable for the most part. Transition metals are unpredictable. You have to look up what these guys are going to do to get stable. They don't always follow the rules. Like some of these transition metals, they make more than 1 charge, but usually the S and the P's are predictable. Which group of elements on the periodic table is most unreactive? The noble gases. Noble gases are good to go. They don't need to do anything to get a stable octet. They have 8 in the outermost energy level. They end up with S2P6 naturally. They don't need to gain, lose, or share. Shielding effect. Shielding effect is like kids in the way. If the teacher's in the front of the room and the kids are way back here, make little circles for students, the teacher would have a hard time watching what these kids are doing because there's so many other kids in the way. This is known as the shielding effect. So if this was an electron that you're focused on out here, let's circle one of these guys. This is our valence electron that we care about. If this is the nucleus, which is positive, the positive pull on this valence electron here would be reduced because all of these electrons are in the way, and that pull isn't as strong. If that pull was on this electron, it would be much stronger because it's closer. So shielding effect is like kids in the way. And we're always talking about the pull from the nucleus on valence electrons. Now, we're going to use that to help us explain some trends. We're going to look first at the size of an atom when we go across a period and down a group. When you go across, most kids think it gets bigger because you have more protons. Again, it's not bigger as you go across, it's actually smaller. Yeah, there are more protons, increasing number of protons. Over here, more protons. This is less on this side. But this is like changing. If here's Giant Stadium and here's a marble on the 50-yard line, it's like taking that marble and making it a ping pong ball or a golf ball or even a beach ball. Changing the nucleus size isn't going to change the size of the overall atom, but changing the nucleus size by adding more protons is going to increase the pull. The attraction between the electrons and the nucleus is going to increase. So that's why these guys get pulled in tighter than these guys. So when you go across a period, they actually get smaller because there's more protons, they exert a stronger pull, and those electrons in the cloud are pulled in more tightly. As you go down a group, it gets bigger. And it gets bigger because we have more and more energy levels. So the size does increase. So you should have a clue about what happens to the size when you go across and why. And it's always increased number of protons. And when you go down, and it changes because you keep adding energy levels. So there's more energy levels here. These guys are bigger than those guys. The next trend that you should be familiar with is ionization energy. Think about stealing electrons. So as you go across, there's more protons on the right, so they're pulling on those electrons more, so it's harder to steal. This, I give the analogy in my class, if I was a teacher in the room, and let's say there's 3 teachers in the room, and somebody wanted to come in and steal a person from the second row of the classroom, the 3 teachers would put up a certain fight with a certain amount of energy. But if there were 10 teachers in the room and somebody wanted to come in and steal a kid from the second row, the 10 teachers could put up a much bigger fight and it would be much harder to steal. So you could think of people coming in and stealing kids as ionization energy. How much energy do you need to come in and steal a kid? But in this case, how much energy do you need to come in and steal an electron? You need more energy when there's more protons. And over here, if you're a person who's going to come in and try to steal a kid from the second row, the teacher's pretty close to that kid, so you're going to have a tough time. But if you're coming in and stealing a kid from the 7th row, there's so many kids in the way that you probably don't need much energy to take a kid out of the last row, out of the 7th row, or even the 6th row. So lower energy here. You don't need as much energy to steal somebody because they're so far away from the nucleus. There's 7 energy levels in the way. So pause for a second, read through the explanations here, make sure that you understand them. And again, it comes down to the same 2 factors. As you go across, it's always more protons, stronger pull. And then as you go down, more energy levels. So we have more electrons in the way and greater shielding effect. The nucleus can't pull on the electrons as much if they're farther away than if they're closer. So if you have lots and lots of energy levels, it's hard. Or it's easy rather to steal an electron because it's so far away. But if you're trying to steal that electron, it's so close, you have to use lots and lots of energy. So high energy to steal that guy, low energy, you don't need much to steal an electron here. All right, electronegativity is a tug of war for electrons. So if 2 elements are sharing electrons, how well do they share? So if I've got element sodium and chlorine here. Chlorine is extremely strong. It's on the right side of the periodic table, so it's got more protons, stronger pull. It's able to pull on electrons. So if they were sharing, and these 2 don't share because sodium's so weak, but if these 2 were to share, the chlorine were to pull, or would pull that electron towards itself, and unfortunately for sodium, it pulls it so much that it takes it right away from sodium. So sodium ends up with a +1 charge, and chlorine gets a -1 because that electron stays with the chlorine because this has such a high electronegativity value. If we had something like water, here's oxygen, here's hydrogen. Oxygen is stronger than hydrogen, but it's not unbelievably overpowering like chlorine is compared to sodium. It's not going to completely take the electrons away. the electrons are going to go back and forth, but they're going to spend more of their time around the oxygen and only a little bit of time around hydrogen. And then around the oxygen, a little bit of time around hydrogen, because oxygen's stronger. So that's what we're looking at here when we're talking about a tug of war for electrons. Do the electrons go back and forth, or do they just get pulled towards a stronger one? Or do they go back and forth evenly, or do they go back and forth unevenly? So as we go across the periodic table, let me pull the periodic table in. As we go across from left to right, let's look again at the second row, all the electrons in the second energy level. Over here, fluorine is super strong. These guys, by the way, they don't need to share electrons, so they don't really count here. But if we look at all the other all the other atoms, fluorine is awesome. Fluorine is super, super strong. Highest En value of the whole periodic table, it gets a 4. It's the strongest. It's stronger as you go to the right because there's more protons, and they pull those electrons more strongly. As you go down, these electrons down here, they're so far away from the nucleus that the nucleus can't really pull on any additional electrons. So these guys have a very low En value. They're not very strong. But as you go up to the top, these guys have a higher En value because the nucleus doesn't have a lot of electrons in the way. So if it wants to pull on an electron right there, it's super close. Maybe there's 1 or 2 energy levels in the way, so that's a pretty strong pull. But over here, you might be in group 6 or group 7. You might have the nucleus trying to pull on that electron way out there, and there's 1, 2, 3, 4, 5, 6, 7 energy levels in the way. So for that nucleus to pull on that electron, it can't really exert a strong force, so that's not very good. So that's a low En value. So as you go down, again, bigger shielding effect, more electrons in the way. They don't fare very well in a tug of war. As you go to the right, there's a stronger pull, so they fare very well. So these guys have a high En value. Finally, what happens to size? Use common sense here. Don't overthink this. If you are a metal, you should be thinking cation. Cations become positively charged by losing electrons. If you lose electrons, you're going to get smaller. Lithium wipes out its second energy level, and it goes down to only 1 energy level. Sodium ends up in 3s1. It wipes out that third energy level. Now it only has 2 energy levels. So it goes from 3 down to 2, and so forth. These all become smaller. Aluminum loses 3 electrons. It becomes really small. These guys, anions, are all nonmetals. How do they become nonmetals? How do they become negatively charged nonmetals? They all gain electrons. So if you go stuffing 3 more electrons, these guys gain 3, it's going to get really big because they repel each other. They spread out. Over here, you only stuff 2 extra electrons in there. So they spread out, but not as much as the ones with 3. And this one only gains 1 electron. So you put an additional electron in there, and again, they spread out. Because all those additional electrons that you add in there, they all repel each other. So they spread out. So these anions become bigger, cations become smaller, and hopefully you understand why.